So hello, everyone out there. Today the tables are turned, and I have the great pleasure to interview Thomas Hillen, who I've had the wonderful opportunity to know for quite a long time. I first met Thomas in Dundee, because for a very long time.
In Dundee?
I'm
Okay.
pretty sure, yeah, in Dundee. Because for a long time, all mathematical roads and mathematical biology intersected in Dundee when Mark Chaplain was there.
Yes, right.
And so we were there for a conference, and we had wonderful conversations, and we got to talking, and we learned that we have the same birthday. And then we learned that Heiko Enderling has the same birthday. So we
indeed.
have three math biology birthdays on the same day. So we, among those, besides a love for having the same birthday, we discovered, a common love for mathematical biology. And it's been a wonderful friendship over the years. So I'm so excited to interview you. Can you please give an introduction to yourself and your favorite areas of research?
Yeah, so my name is Thomas Hillen. I'm a faculty member at the University of Alberta. And I did all my degrees in Germany, like a PhD and master, and also the habilitation degree. So some people know what that is and other people don't, but anyways. So this was all in Germany. But then I had a postdoc time in Salt Lake City in the US. And this is where I met Hans Othmer, who was my supervisor there. And I also met Mark Lewis, who became a good friend then over the time. And then in 2001, I moved to Edmonton to start faculty position at University of Alberta. And so in all this grown-up period of my career, I worked a lot on partial differential equations. I was very mathematical. I used semi-groups, and I proved lemmas, and did all these things, and worked on chemotaxis. And so my chemotaxis work has actually become quite well known. So this worked really well. But then when I came to Edmonton, I thought, well, we have all these tools and all these techniques. Why don't we do something useful, or why don't I do something useful with it? And this is how I got into the modeling of cancer.
Okay.
So I thought cancer is a complex system, and what is the language of complex systems? It's mathematics, right? So then I thought, okay, so these techniques which I have learned during my education, I would actually like to use them and develop them for the benefit of cancer research.
Oh, that's a beautiful segue into really getting into how you got from mathematical biology to mathematical cancer biology in particular. Right. And I can certainly see chemotaxis being a good bridge. And so you basically chemotaxed from regular biology to cancer biology.
Yes.
Have you seen any surprises as you started developing and adapting all these techniques you already learned in the cancer biology field?
Yes. So the biggest surprise is a little bit of a negative, and that is that the modeling we do, or the results we find, it's very difficult to get them into the clinic, to get doctors or medical people to recognize these results and to act maybe upon them, or get them into the clinic. And it took me a long time to realize that this is a long process. So first of all, you can't do this alone, particularly not as a mathematician, so you need collaborators in medicine. But this is not enough, right? You need to prepare things for a clinical trial. And clinical trial is a very complicated thing, right? I don't know if you're involved in some.
Fortunately, not yet.
Not yet, yeah, and same for me, right? Not yet. But I work with people who work with clinical trials, right? And it's a really long step. You need a well-defined treatment methodology. You need to contrast it to some established treatment methodology. And then you need to recruit patients, and you need to get ethics approvals, and you need to pay people who do it, right? You need to pay the people who do it, and you need imaging data, and so this is a very complex thing to get a new result into the medicine.
So, does math modeling need to get all the way to trial to make an impact in medicine and in cancer biology?
So yeah, I recently read a wonderful paper by a pharmacologist about modeling in mathematical modeling for cancer. And they said there are essentially two approaches. One is a data-driven approach, where you first look at the medical data and then do modeling. But the other one is a phenomenological approach, where you look at the biological process and design a model for that process and learn from this. And this is essentially what I have been done in my career all the time. So I usually start with a process, for example, metastasis, or how the immune system interacts with metastasis. And then make a model, and then use the model to explain biological observations.
And have you found, as you said, kind of worked from going from working alone, realized you had to work with a biologist or with a clinician. Have you found that mathematical framing you bring with you has changed the conversation with the biologist, or later on maybe we've kind of infected them and it changes the way they're thinking about their work?
Well, first of all, I would say the conversation with biologists changed my modeling.
Oh, yeah.
Because I noticed that often we get away with very simple models.
Mm.
You might have noticed the same. So I come with my transport equation, PDE framework, and then sometimes it's just a logistic equation which can explain the data. So I think simple is good. Simple is a good thing.
Simple is good, but not too simple.
Not too simple. Right.
So I really love that too. That really brings to the point that really reality checking with the biologists we're working with helps us identify if we've maybe oversimplified a little bit, we're missing something key, or we have the next thing to look for. In your current models, what gets you most excited right now as you look at the models and the projects that you're working on today? Like, what's the one that you say, oh my God, I got to get to the office. Let's do this thing. This is the advance is just right around the corner.
Well, this is definitely the tumor microtubes.
Oh.
So it has to do with glioma, so brain tumors.
Okay.
And in 2015, there came out a paper where they were able to follow the invasion of glioma in a mouse brain live, on a living mouse, which is very crazy. So they have to open the skull and they put like a window screen there, and
cool.
And they film it and they can see how the brain tumor advances. And in that research, they found that these gliomas send out very thin microtubes, very thin protrusions, like needles, and they call them microtubes. And then these form networks, and these networks can relay signals. Oh. So then essentially what happens is like a brain grows in a brain, kind of. And they communicate via calcium signaling. And I read this in 2015, and I thought, I have to do this. This was just such a moment you were asking for. Like the hairs on my neck got up, and I thought, I need to do this. I need to model this.
Wow.
This is so interesting. And so then it took me like until last year, so which is 8 years, to come up with a model for this process.
Oh, that's fantastic. And so it's primarily about the communication along these microtubes, or do they guide migration or anything else?
Yeah, so the migration is important bit, because these microtubes are so thin, you don't see them in imaging, right? And then if you take out the bulk tumor which you see in an image, you might leave the network behind. And this is one reason why the brain cancer comes back.
I see.
Yeah.
So you get to connect to your chemotaxis roots in this project.
Yeah, right, exactly. This plays a role as well.
And I guess all roads come together in cancer also. It seems like it uses every bit of biology that we know.
For sure, it does, yeah. Right.
Let's see. Kind of going more from your background and your research, that's an exciting project. Do we have a preprint that we get to read? Will we maybe post it up?
Well, this is actually already published.
There we go.
Journal of Math Biology.
So we'll make sure we need to put it into the comments somewhere on this conversation. Kind of switching more now from you and your career arc, what would be your advice to a new scientist, a new mathematical biologist entering our field today?
Yeah, so my experience is that a young person, like let's say a PhD student, during the PhD career, they need to decide who they are. So it's a little bit like a search for your own gender or for your own identity. So are you a mathematician, a biologist, a computer scientist? And these drawers or these fields require different action, I find. So if they want to be a mathematician, they need to publish in math journals. So then something like publishing in PLOS Computational Science or iLife or whatever, these are good journals, but they're not highly recognized in math departments. So then the journal needs to be called SCIEM, Journal of Applied Math, or right? So some more mathy recognized journal. On the other hand, if people see themselves as a computer scientist, they have to go to the corresponding conferences, right? In computer science, the conferences are important. And you need to get abstract accepted in these conferences and so on.
That's really great advice. Any other advice for a new learner or a newcomer or someone coming in from another field where they've already been working?
Well, definitely you have to be excited about what you do, right? So it really needs to capture you in your core. This is what I want to do. Otherwise, I mean, you will always have moments where you doubt yourself or they think I'm not smart enough, or I can't do this, or I don't have the resources. So then the inner motivation, the inner strength needs to be there to get through
It
this.
helps you power through and
Power
and
through.
kind of reach that thing.
Yeah.
Well, thank you so much for joining us today, Thomas, and
Yeah, thank
giving
you
me
very
the
much,
opportunity
Paul.
to interview you. It's been a lot of fun, and I've really enjoyed our conversation.
Yeah, likewise. This is great.
All right.
Thank you.
Thank you.